All right, so where were we? Yeah, I'm getting solar panels installed in my house, so I had to go and talk to the guy who's doing some of the work. So yeah, I think I had just kind of given you a rundown of what I would do to look at the depression question. And let's see, did we adjust this properly? Yeah, this is referring to the proper cells. Let's see, did I fix the standard deviation too? No, I did not. So 26 through 45 is what we got. This should also be 26 through 45. So that refers to, this row here. This is the first depressed person. And this should also start at row 26. And this should start. Oh, then this is the same, because this isn't referring to the depressed cells. It's referring to the standard deviation cell and the count cell. So you don't have to adjust that. So then I'll take these four and copy, Control C, Control V, paste, and now you have a nice little summary of various things. So let's, rather than looking at all the data and being like, oh, which one looks like it has the biggest difference, let's be theoretical. And I think you guys, you said this is what you kind of articulated, Abby, in your email, that you wanted to look at the average size of emotion or some of the pupil during different emotions. So that would be this. This is the sad average size during the entire trial, and the happy average size during the entire trial, etc. So if I scroll down, it looks like there's no difference between those. And there's no difference between each other either. 54, 54.3, 54.0, 54.9, 8. They're all pretty close. And that makes sense, again, because the subject does not know what emotion it is for the vast majority of the trial. It's like a 10-second trial. They figure it out at the very end. They press the space bar. So the difference score would be more interesting to look at, I think, because there you might actually see differences if the pupil is contracting or dilating when they're realizing what emotion it is at the end, and then comparing that to whatever size it was at the beginning of the trial. That's what you have here, these sad, happy, fear, and angry difference scores. And I would actually start with the difference average score, which is just the average across all emotions, and then look at the threat, and then look at individual emotions, because there's going to be a lot of noise in these individual emotions because there's just less trials per emotion, versus looking at the entire, all 40 trials. This is a much more reliable number. So let's look at this first. I would look at this first. Difference average across all 4 emotions. And you're going to see 0.05, 0.02. Okay, is that reliable? Well, so on average, the non-depressed people, their eyes are constricting by 0.05. The depressed people are constricting by 0.02. Is 5%, 5.5% difference different than 2.3%? I don't know. Let's look at the standard error. So that's about 0.01 for both groups. So is 0.055 different than 0.02? I don't know. This is kind of borderline. This is pretty close, actually. This, I bet you this is not quite significant, but it's like a trend to almost significant. If you want, we can do a t-test real quick just to see if I'm right about that. So I'll grab the first, folks. Is it these guys? Yeah, the non-depressed people. I forgot to grab. Then you type comma. This is how you run a t-test in Excel. You might as well learn. And then I'll grab the depressed people. Select all them. I'm holding down Shift and using the arrow keys to keep going. If I don't hold down Shift, it just moves the cursor like this, you see. But if I go to the starting point, hold down Shift, and then it helps me select them all. So that's all 20, and then I'm going to hit comma. Two-tailed test or one-tailed test? Well, I have no idea what to expect, whether depressed people would have more constriction or less constriction or dilation or whatever than non-depressed people. I just am exploring for a difference. So we definitely want a two-tailed test. Comma. And there's 3 different types of t-tests you can do. The first one is paired. This would be as if like you're doing a repeated measures design and you have 2 conditions with the same subjects. That you would use a paired t-test for that. A 2 sample with equal variance assumed might be useful in some cases, but in all the research I do pretty much, you don't want to assume that your two samples have an equal variance to each other, because usually the patient group is going to have a higher variance than the non-patient group. So you don't want to assume equal variances. So we always use version 3, which is non-equal variance assumed. And we hit enter. And oh, look at that. 0.02. That's significant, folks. That's cool. All right. So you guys can try and redo this in SPSS if you can. If you can. If not, we can do it together, maybe during lab meeting. But this would be something to write your mother about or put on your poster, that there's a difference between the depressed people and the non-depressed people in terms of how much their eye constricted at the end. Now we could look further and see, is that more so the case with the threatening faces or the non-threatening faces? And we're going to see that it's more so for the threatening faces, ever so slightly. That's significant, 0.01. That's not significant. But really, if you look at the differences, it's 0.059, 0.052, 0.02, 0.02. So I would say this is probably noise. The fact that this is significant and this is not, I don't really believe that there's much of a difference here. It's just one is on the right side of significance and one is the wrong side of significance, but they're both pretty close to being equal. One way we could compare the differences is to compute the effect size there, but let's save that for another time. So this is kind of your depression story here, I would say. And we can look back then at individual emotions, and it seems like it is driven by these two, 0.01 and 0.001. This is quite significant. What's this? Fear. Okay, so the one for fear is quite different. Fear is kind of driving this result here that we found to be significant initially, which I just bolded. All right, well, that's good. That's to get you started for that. Now, you want to do a scatter plot. Okay. Or you want to look at correlations. Okay, right. So let's do that. So, should I try to teach you to do this fast or teach you to do it well? I'll teach you to do it well. But I will hurry because I don't have a ton of time to talk about this right now. Gordon primarily pays me to teach, so I have to go get ready to teach. That's why I have to hurry talking about research. I love to talk about this stuff, but yeah, unfortunately, I can't spend as much time on it as I would like. So how are you going to look at the social anxiety stuff? Basically, what you're going to do, SIAS. I think this is social anxiety questionnaire of some kind, and you're just going to correlate this with some of the stuff, like the average pupil for man, average pupil size for women, or the difference score. I would actually probably look at this. I would look at the grand mean overall, and then I would correlate it with the difference score. Two correlations, one for the grand mean, to see if social anxiety has anything to do with the average pupil size, which I doubt it does. But then look at the difference score for men and women. So again, if social anxiety has something to do with making you extra afraid of threatening stimuli, especially if you're a male, this might be more threatening for males. Males might be more threatening, cause more pupil constriction or something than females for people with high social anxiety. So you might find a correlation here with this difference score, where the greater the difference, the more people get extra afraid of men is related to more social anxiety. That's my hypothesis. I don't know if you guys agree. Maybe you come up with a better hypothesis. But that's what I would look at. So, but I think that might be mostly the case for the men in the group. So we might want to first sort by sex. So for this, what I'm going to do, integrated 2. What I'm going to do is say integrated MDD. So this is the MDD question is answered sort of in this spreadsheet. I'm going to send you guys this spreadsheet. If I forget, remind me, please. Copy. Then I'm going to copy the whole spreadsheet over here. And this is integrated data social anxiety. I'll call it. Okay, So we'll sort our data in order to address the social anxiety question in this spreadsheet. I'll grab all the data and I'll sort by, oh, gotta remember what to sort by. I don't know what SOCFRA is. It might be some sort of social anxiety questionnaire, but I think SIAS is too, BY. Here's a novel idea. Why don't I check that? What if I just correlate SOCFRA versus SIAS? If I'm right that they're both social anxiety measures, it should be a pretty high correlation. And it is 0.85. Dang nabbit. All right, so you can take your pick of these two questionnaires. I think I remember Lauren used the SIAS maybe. She suggested that to me. So Lauren Rudder, who's the driving force behind this project. So let's go maybe with that one for starters, which is column BY. So I'm going to go back and select everything. And why did I just sort by column BY? I don't want to do that. Let's sort by sex. Because I think it might make sense to do a separate correlation for men versus women. This is my master plan. I didn't even articulate until now. Column B. So guess what? Oh boy. All the way down to 28 is the women. The men, we only have 7. Oh, we have 17 men. Not bad. All right, so what I would think is we'd want to run a correlation with just the men and a correlation with just the women on this difference score between male and female stimuli. We can also look at the grand mean. And for these fear difference scores and angry difference scores. This is going to be fun. Lots of actually interesting questions. So how are you going to do this, though? How are you going to run your scatter plot? What you could do is do what I did before with the social anxiety thing you just saw. I said equals, Corel, blah, blah, blah. I select my first variable, and then I select my second variable, if I want to correlate these two things with each other or whatever. And then I just hit enter, and it's going to tell me a p-value, 0.97. There's no significance there. Oh. No, sorry, 0.97 I think is the R value, which is extremely significant. 0.97 is like almost 1, almost a perfect correlation. That's because I selected these two variables, which are the average size of your pupil for male stimuli and the average size of your pupil for women's stimuli, and they're very, very closely related to each other. So it comes out to 0.97. But that's not a good way to run correlations because you really want to see the data. You really want to see a scatter plot of your data because if one subject, especially with sample sizes this small, if you have one massive outlier who's very high or very low on both variables, it can drive a significant correlation, and it's really just you have this one wonky subject, and it's not a true finding. So you want to look at a plot of your data so you can know, is this driven by one wonky subject, or is this like a general trend, like I'm seeing a cloud of dots spreading out with a given slope or whatever. So I will show you how to run a correlation in MATLAB. And this will probably, Abby, you have to do these because I don't think everyone else has them. So I'm going to create a little script for you. And what you would do is grab some data. I'm thinking here. So grab the SIAS data. Okay, now it says NA. Let's actually change that to NaN. NaN. Let's just delete. I don't know. Let's do NaN. Sorry. Can't decide. I'm trying to remember what MATLAB is going to like. And I'll just put NaNs in all these missing slots. Right. So going back to here, we'll grab our SIAS data, Control C. We're going to say SIAS equals, going to put brackets, we're going to paste it in, and then put a semicolon after it. Enter. Okay. So what that's going to do is when I run this program, soch plots, I'm going to put it in the pupe stuff here. Soch plots. It doesn't like, yeah. It's angry at me because I saved it with the wrong kind of name. I think you can't have a space in it, is why it was mad. So we'll go here, find it. We'll change its name, and then we'll open it from here. Okay, here it is. Social plots. Okay. So now if I run, change folder, sure. Okay, see it says SIAS. And if I type SIAS, boom, it's all these data that I put in. Cool. All right. Now if I say clear, that kills all the variables you created, and now it's gone. See, but if I run the program again, oh, it automatically creates it again because it executes this thing I said. It sets SIAS equal to B, these numbers in brackets, okay? So now the next thing I'll do is, why don't we make another variable that we're going to correlate, which is called one of the pupils thingies. All right, so let's take the grand mean of, how big your pupil was during the task. Control C. So we'll say pupe mean equals. And then I do the little bracket thingies, and then I paste in the bracket thingies. I'm just hitting delete so that the bracket thingy is on my last line. And then I do a semicolon. And now, okay, I'm going to clear, kill all my variables. Now I run the program. That noise is the solar panel people. You can hear that. Now I have these two variables, SIAS and pupe. All right. So now what I can do, this is fun, scatter plot. SIAS is going to be the X variable. Pupe mean is going to be the Y variable. Oopsie. Oh, you bum. Sorry. Plot, and I'll tell it to make little O thingies. Oh, yeah. Look at that. That's our plot. That's truth right there. So this is social anxiety here. And this is pupil size here. What do you think? If you were going to draw a line of best fit there, would there be any relationship? Would there be a significant correlation? I don't know what you thought, but I would guess no. I don't think there's anything there at all. So there's no relationship, it looks to me. Now, there is a way to do correlation in MATLAB. How do you do that? Corel. Help Corel. Help Core. Yeah. Oh, core coef. This might be what we want. Of R value, yeah. That sounds nice. Let's try that. So what if we did say core coef SIAS pupe mean. Ooh. Oh, you little bugger. It doesn't like the fact that we have some nans in our data set. All right, so I don't have time to work on this anymore, unfortunately. So I'm going to have to tell you, Abby, mostly, and other people if they want to help. You've got to Google this. I could Google it right now, I'm sure, and find the answer within 5 to 10 minutes of how to deal with nan values in how to do a correlation in MATLAB with nan values. I'll just click the start. Correlation. So I would use the command is most likely to be a good way to do the search. Core coef MATLAB nan, and it's going to compute correlation of 2. So this is probably the one you want to click on. So Google that, and you'll be able to figure it out. So what I would want to do ultimately is use that. Yeah. So what I'm going to do is add to the script here that we've been creating that little command there. So that is going to automatically generate. Watch if I hit clear. All right, where's our plot? Kill it. Get out of here. So now when I run this program, booyah, it creates the plot for me automatically. Creates both variables, then it creates the plot. All right, I was going to do one more thing, which was add to the plot text. How do you do that? I forget. Just Google it. Just say how to add text to a plot in MATLAB, and it will give you some lovely code for how to do that. Add text descriptions to data points, and it'll give you a bunch of examples here. And this is what we want here, where it says sign of whatever. We don't want to write that. I just wanted to make it nicely tell us what the correlation coefficient was for the plot on the plot. So you run this, make a little text thing that says correlation coefficient equals, and then whatever it is, and then you're going to be able quickly have a sense of the visual and the actual R value. And you'll know if there's a relationship there, which here it looks like there's not, but it'd be nice to know the exact value. And maybe my eyeballs are wrong, and it is, a big R value. So that's what you can do. But then you can easily manipulate this code. You can copy and paste your code and make more code and just change which the variables are, run the thing again, and create more plots. And it'll automatically generate the correlation coefficient for you. I know that was kind of quick, but why don't you try and get started and let me know where you get stuck, and we'll work on it some more before Thursday.